Hopefully by the end of this week, I have both of our Chapter 3 quizzes graded and back to you, so you know how things are looking for you in terms of grades, because that's probably it on grades until the final. Okay, seniors, that's it. Yay. You guys have done what you needed to do, so hopefully you finish strong there. The reality of kind of what we're building towards this week, of course, is still Friday, right? So seniors, you guys have one more thing left in terms of stuff to do, but your calculus quizzes and things are all done. So we still have our CU60 final on Friday. And what I did yesterday is I jumped onto Canvas and I created the quiz. And obviously, there's no questions in there yet. There won't be until Friday morning. But you can click on that quiz. You just have to go like down to quizzes. Okay, it's the only one sitting there. And that's where it will be housed. This is what we'll do on Friday. You'll bring a device with you. We'll take the quiz. You will bring your calculator. You'll bring your trig cheat sheet, which has unit circle on it, and that should be enough. So we'll do it in class on Friday. And what I did attaching to this quiz to help it all kind of be in one place rather than keeping it all over the place is I put a link to the initial review, the CU Denver provided review, a link to the solutions for that review. But I told you which questions to do. Okay, if it's not here, don't do it. Okay, if it's not in that list, don't do it. Now, you might feel, though, that 13 questions, there's only like 13 or 14 review, like there's like one of each, or maybe two of each at most. You might not think that that's enough. So what I'm hoping to do tonight is kind of like go through this list of topics, and I'm going to scoot it up a little bit. Go through that list of topics right there, and kind of give you some examples in addition to what CU Denver has provided. But let me really quickly pull this up so you can see. Is it this one? Yeah. See what kind of questions we're dealing with. This is the review solutions. It's just the review with the answers kind of written on top. Evaluate sine of 4 pi over 3. Yeah, cotangent. All right, cool. You know, whatever. Inverse sine of negative radical 3 over 2. Some of them do have a none of the above option, which I know is really, really frustrating. I think, and don't quote me on this, but I think the final itself, that's never an answer. So the right answer should be there for you. Convert 315 into radians. Convert radians to degrees. Yeah, domain and range of some functions. We've talked about that a little bit. Skip it. If cosine is positive and cotangent is negative, then where's theta? Well, cosine is positive, so it's first or fourth. Cotangent's negative, so the sine of x and y are different. Oh, it's in the fourth. Find the reference angle for it's really not bad. And again, we're skipping the things that we don't have to worry about. Identify the phase shift. Amplitude of 4, period of pi. Like it's pretty straightforward kind of stuff. So that's pretty good. But you might feel like you don't have enough of a certain topic, so I'm happy to kind of make up a handful, probably less, of each of these. But evaluate trig functions at unit circle angles. Evaluate some inverse trig. Some domain and range, which we might have to recap tomorrow. That's okay. Given the sine of two trig functions at some angle, where is it? Given theta, what's the reference? Literally locate an identity on the cheat sheet, like find it and tell me what it is. You don't have to use it, which is good. The transformations with phase shifts and amplitude, stuff like that. Number 8, which we're going to do today, and then 9, solving trig equations, basically. Sine of theta equals 1. What's theta? Like that. Yeah.
So we get to use our trig functions and the unit circle on the.
Yeah. For sure. Yeah. Making it easy on us, which is nice. Okay. So it's not out of any points yet because there aren't any questions in there yet. What I will do Thursday nights at some point is I will unpublish this quiz so I can make it. Okay. So the thing that you should do today is jump onto here, download the review and the solutions and leave them up as tabs on your computer. Okay, because eventually, sometime tomorrow night, I'm going to unpublish it and you won't have access to it anymore. Now, if that happens, you're like, oh, I don't have the link anymore. I'll just send you the link. That's fine. Maybe I'll put it on an announcement or something so you can always get to it. But this thing itself will disappear for 12 hours or so between like 8 p.m. and 8 a.m. or something. Cool. So I have one thing to teach you, and it is number 8. We're going to talk about what polar coordinates are. But first questions, yeah.
Will we be able to use a calculator?
Absolutely, yeah, for sure. I don't think you would need it for much, but you might like it. Yeah, you might like it. Especially like domain and range of a trig function. Maybe you don't know it, then graph it, look at it, right? That could help. Yeah, for sure. So bring that calculator with you. Other questions about Friday? Cool. So what I want to do today and tomorrow, today I'm going to teach you the new thing. And then tomorrow we'll just have a review day for it. Okay, and we'll work through whatever questions you have. Hopefully I'll have some extra practice for you and we can kind of talk about them. I know it's listed there as a final. It's not going to be weighted anything like a final ever would be, okay, because this is months and months and months ago that we were working on stuff like this. I care more about the calculus. And so our final that we actually take, so non-seniors, the final that we actually take will just be a chapter 4 test. During our Friday the 21st is when our final is. We'll have just a chapter 4 test. It'll be weighted like a test, not like a final. So it'll be out of 100 points, but not like 200 or 300 and make a huge difference. So if you're worried about what your grade might be, talk to me. We'll figure it out. Okay. I want to get you the grade you deserve as best we can. Good. Okay. Now, before we get to polar coordinates, I want to get, well, it's really not a big deal. I'm not going to stress about it. We might as well do it, though, so we can wrap things up in chapter 3. Take out the Unit 3 guided notes one last time. And I just want to give you the derivative of the inverse. I want to give it to you so you know what it looks like. So the last one that we just had, yeah, the Unit 3 with all the product rule, chain rule, quotient rule, exponentials and logs. Turn to page 227. 227. Super briefly, not going to spend a ton of time on it. It's going to give you a nice little rule so that you've seen it, but it is not something that happens very often. But the process in finding it is something that we will actually work through next week. I'm not going to prove it to you, I'm just going to give it to you, but I wanted to talk through what they're going to have us do in order to do it. Okay. So you don't have to look at 226. I'm just going to pull it up for a second. What they start to get us to think about on 226, again, you don't have to look there. You can look at 227. You can look up here for a second. Is they give us a function, some function of x. Of course, we can find the inverse of that. Now, the inverse of a function is not always a function, right? Because we're switching x and y. So you think about like a parabola being a function. The inverse of that kind of looks like this, right? It looks like the sideways version of a parabola. And that's obviously not a function because x and y have now switched. And you've got like, instead of y equals x squared, now you've got x equals y squared. But we can still write it as f inverse of x, even though it might not be a function. We can kind of still use function notation. But either way, what we've got, something reflective of the line y equals x. We're switching x and y, whatever you want to think about it. What really we've got now here on 227 is the fact that f of f inverse of x is x, right? Take the function, plug in x into the inverse, and then do the whole idea of a function's inverse is to kind of undo what's happened. And I'm not going to do it right now because we'll do it next week. But I might have said this in passing before, but when you have an equation that's absolutely true, that is absolutely true no matter what we're dealing with, you can add 1 to both sides and it's still true. You can divide by 3 on both sides and it's still true. You can square both sides and it's still true. What eventually we'll do next week is we will differentiate both sides. I can take d dx of the left side and see what I get and do the same thing to the right. Okay, I can take the derivative with respect to x of just the expression on the left. Same thing on the right. And we've actually, don't write this, but we've actually been doing that the whole time. When I say this, right? And I say, oh, what's the derivative of y with respect to x? What I've really done is I've taken the derivative with respect to x of y, the derivative with respect to x of x squared, the derivative of y with respect to x, okay, the derivative of y with respect to x is 2x. All right, we've been doing that the whole time. We just didn't need to really write it down. So that's what they would do to prove the following. I'm going to save us the trouble. What I want you to write down in that little box is this right here. Again, if I had lots and lots of time, we would play around with these ideas. We would prove it ourselves. But given some function of x, right, y equals some f of x, whatever it is, and the inverse, we need both. We need both of them to do. If I want to find the derivative of the inverse, but maybe it's kind of tricky because it's not a function, or maybe I've got this really complicated inverse, and the derivative of the function might be a little bit easier. We actually end up with this composite setup. Okay. So really what you're looking at there, second line down, the derivative of the inverse is how I'm going to read that, okay? F inverse prime, sure, if you want to read it from left to right, but when I read F inverse prime of x, what I'm really thinking, the derivative of the inverse, it's 1 over, and it's just a chain rule kind of thing. The derivative of the function, but instead of it being just x in there, we change x to the inverse. Like I find the function, you gave it to me, I find the inverse. Instead of doing just f prime of x and doing 1 over that, I'm going to do f prime of, and then every x I'm going to change to the inverse. So kind of fun. Not a terribly difficult process to do it. You'll actually see that that's what I'm going to call number 11. Okay, I'm going to take d dx of both sides of an equation. We're going to solve it. And really it's for equations that aren't functions, right? Not defined to be y equals some function of x. And that's called implicit differentiation. We'll do that next week. But I just wanted to give that to you. The other thing that's in this unit that I'm not going to actually do in the unit, we'll come back to it, it'll kind of happen naturally as we go. Functions that are continuous are not necessarily differentiable everywhere. Okay, if a function is differentiable, it's definitely continuous. If you want me to find the slope of a tangent line at the point's got to be there. But I can't always draw one single tangent line. And so the end of this chapter talks a little bit about relationships between continuity and differentiability. Okay, but I want to get you ready for Friday, so that's going to be my focus. So you can take those guided notes, you can put them away for right now. Hold on to them though. You might want to hang on to those. And just open up your notebook somewhere. Literally, you just need like a page at most for today. And what I want to do is I want to teach you how a different graphing system looks. Let's see if I can do this without spilling the beans too fast. Don't look. Okay, now you can look. Okay. Okay, polar graph. And we're just going to focus on single coordinate systems. We're just going to look at give you to a point, how do I graph it? So that's just polar graphing. The kind of graphing that we're used to, right, was a grid. And you don't necessarily have to draw this if you don't want to, but right, when we think about graph paper, it looks like this. And we would define a center somewhere, right? We say, okay, there's the y-axis, there's the x-axis, and we would just pick a middle of an infinitely humongous, perfectly flat kind of space. And to design a way to get to a point, let's say this point right here, right? Let's say the points 2, 3, right? There's the point 2, 3. How do you get there? Like simplify things in your mind. Don't overcomplicate it. how do you get from the origin to that point? But like I want to take a path, like that would be slope. Like that's how steep the line would be to get there directly. So what do you mean rise over run? Because you say rise over run, I think slope. Yeah, like you take like two separate linear paths, right? Like you follow a red straight line left and right, and then you follow another red straight line up and down. It doesn't matter what order you do it in, you still get there. But usually we do the X direction first, and then we do the Y direction. Now, but we could do it either way, right? I could go this way and then this way. Or I could, right? I could go this way and then that way. And either way, I get to the same point. What shape did I just draw?
Rectangle.
Rectangle, yeah. Now, it could have been a square if I went the same distance, but every square is a rectangle, right? Not every rectangle is a square, but every square is a rectangle. And so the system of graphing that we've always done, okay, has been rectangular. Okay, we've been doing rectangular graphing our entire lives. That Cartesian plane, you know, that's filled with a bunch of squares, right? I could take two different kind of rectangular paths and get there. Okay, what we're going to do is we're going to envision a very different looking graph. Where instead of it being rectangular paths, like where I can draw a bunch of rectangles to get to certain spots, we're going to do something else. Okay, and so you don't necessarily have to draw what's on the left here, but I would highly suggest you draw what I'm about to. You know, create a little set of axes. It's super small, it's fine. And of course, there's an origin. Right? We've got an x-axis and a y-axis. All that stuff is still true. But how we get to a certain point is not necessarily going to be the same way we get to it. Now, the point 2, 3 still exists. It's there. I can go right 2 and up 3, whatever that means. But how we define that point is not going to be rectangular. Instead, what we're going to do is we're going to envision ourselves, and I think the visual side of this is going to help. Imagine that the origin, right there. Okay, we're looking at the origin. Imagine that you're doing that. And here's the best idea that I have. Imagine floating in space, and you are looking down onto the North Pole. Okay, imagine looking down at the Earth, and you're looking down at the North Pole, and it's right here. Okay, and you're looking at the Earth, but there is a map of the globe kind of drawn on top. Like all the oceans and land, it's all gone. And instead, what you see is kind of a grid of the Earth. Now, we know that the Earth isn't exactly spherical, right? Because the rotation of the Earth going as fast as it does squishes it out at the equator, right? It's not a sphere. It's called an oblong spheroid. Pretty awesome, right? The distance from the center of the Earth to the equator is significantly longer than distance to the poles. Now, when I say significant, I'm talking about like some collection of miles, right? It's not huge, but it's big enough. And so when we look down at the Earth and like there's a grid kind of laid over the top of it, straight lines are not going to work, right? So imagine it's a sphere. Instead, what we can picture, hopefully, maybe you could see like the latitude and longitude lines drawn on the Earth itself. Okay. Now the problem is that if we tried to draw the longitude lines, right, they would like go out and then come back in, right? They would go out and come back around, like it would kind of hook around like that, right? So that's hard to draw in 2 dimensions. So I'm not going to draw any of the longitude lines. I'm just going to draw the latitudes. Okay. So North Pole, that's 90 degrees latitude, right? And then down we go. And as we make our way down the Earth, what happens is this group of concentric circles kind of work their way out, right? Because you've got like 89 degrees and 88 degrees and 87 degrees and 80 and all the way down, right? Can you see that? Can you picture what I'm talking about? Okay, cool. But let's imagine that the Earth is infinitely large. And that at no point does it ever get to the equator and then start to curve back around. Imagine that you're looking down on the North Pole and it only gets bigger. A group, and I'm going to try to draw these as best I can, you do the same, a group of what are called concentric circles evenly spaced out apart. So the space between those circles, I'm trying to draw that evenly. I'm just going to draw this, but it would go on forever, right? Or let's say like this is, and we can kind of mark them off, 1, 2, 3, 4, and so on like that. The polar graph paper looks like that. Okay, polar graph paper. Is not the same as rectangular graph. Okay, this is what polar graph paper looks like. Okay, where there's a center called the pole. Okay, and yeah, I can draw like an x-axis and a y-axis, but the reality is that that's not really what matters to me. I want to take a path to get to a point in space. And let's say I picked this one right there. Hey, who cares? I'm just going to pick one. Okay. And maybe, there's an XY way to get there, right? There's an X direction and a Y direction. But the problem that I have is if I want to take a red path from the origin to that point, it's not rectangular. It's not drawn with straight lines. So let me ask you this. How do you think we could take a red path, a path that is drawn in red right now, to get from the pole in the center to that blue point?
Go over to 3 and then.
So get yourself out to the right circle, I guess you could call it, and then take the arc to get there. Now, of course, that might not be the straightest line, right? Shortest distance between 2 points is a straight line, but it is a way to get to that point. And so what I want to do is, instead of defining it like this, which is xy, right? This over here is xy. I want to define that point right there by doing exactly what you did. Like, get out to the correct circle, and then let's open up an arc and get there. How do you think we could measure where that point is based on those two things?
X and like the radius.
Right? Let's get ourselves in the X direction moving out, and then let's open up an angle to get there. Now, since we're talking about starting at the center of a circle and going to the edge, X is kind of arbitrary. Let's pick a distance that actually means start in the center of a circle and go to the edge.
R.
The radius. That's the first part of the coordinate, is tell me what circle I'm on. Get me to the right circle. Do I go to circle 1? Do I go to circle 2? Do I go to circle 3? Do I go to circle pi? Do I go to circle e? Do I go to circle radical 2? Whatever, right? Get me onto a circle somewhere. Because we know, I could plot the point 2, 3, and great, it lands really nicely. But isn't this right here also a point in space that I can get to? It's maybe not a whole number, but I can still get there. It could be rational, irrational, I can still get there, okay? And then instead of like measuring this arc, right, let's go to circle 3 and then let's do this, right? Let's like start here, go out, and then open an angle. We could measure that arc, but that already has to do with what circle I'm on, right? And I kind of want to think about like what would happen if I opened up a certain angle. Like, maybe I want to be here or here or here. Right? I could be at any of those purple points. And the angle that I open is going to get me into the same kind of space. I just have to pick the right circle. So instead, let's just worry about the theta that we open to get there. Okay, rectangular graphing is xy. Polar coordinates, and that's what we're going to learn. Okay, that is r theta. And that's what they're going to test us on Friday. And section like chapter 9, section 4 or 5 or something in the Precalc textbook gets into this. There's a lot in that textbook we did not do, okay? We didn't get to all of the trig identities and formulas with like multiple angles and sum and difference and products and double angles and half angles and all sorts of stuff. We didn't do law sines and law cosines because that was geometry. We didn't get to vectors at all. Anybody that's taken physics, you've heard vectors before, directed line segments. Chapter 7 is all about matrices, right? A matrix, an array of numbers and letters, helps us solve linear systems in multiple variables. Chapter 8 is all about conic sections, how you draw things, like how you can slice through a cone and the kind of shapes you get, which are circles, ellipses, parabolas, and hyperbolas. So much we didn't do. And this is one of those things, polar coordinates. What's nice about this is it's actually fairly easy to make the switch from rectangular to polar or from polar to rectangular. So what I want to try to do today is help you make the switch from one to the other. And so let me do this. Let's say you are at a point. Let's make it nice. Let's go to the point xy. Let's go to 1, 1. Go ahead, draw this out. Let's say they give us a rectangular point, and that point is located at 1, 1. Okay. So this is our normal Cartesian plane, xy. What I would love to try to do is go from rectangular to polar. I want to go from xy to r3. And this is the skill that they're going to test us on Friday. Yeah, there's a lot more to it, and I'll give you the other direction too, just so you have it. It gets into like, there's a trigonometric form for complex numbers that has to do with polar stuff. Really, really cool stuff. So the question is like, okay, if that's the point in space, how do I get myself onto the right circle to get there? Is it radius 1? Is it less than 1? Is it more than 1? What is it? And then what is the angle that I have to open up to get there? Question first, yeah.
What does that top left red word say?
Rec, like
okay.
rectangular.
Okay.
I just didn't write the whole.
Thank you.
Okay, so we're starting in a rectangular graph, and I want to get myself over here to like the exact same point. Like there's a point right here. How do I figure out what circle I'm on and what angle it takes to get there? And really what we have to do is measure the radius of the circle that would get me to right there. I need to measure this length. Right? Because the imaginary circle that this thing is on, looks something like that. That was actually pretty good. I'll take that. And then I want to know the angle that it takes to open that up. So what do you think? If we know x and y, how can we figure out the radius? Yeah, right? And here's what we know is that r squared is equal to x squared plus y squared. So what's r? Not this, don't worry about this, but just in general, right? A squared plus b squared, right? There's x, that length right there. There's y, that length right there. It's just a right triangle, right? It's just right triangle triangle Pythagorean theorem. So that'll give us r squared. So what's r? Not of this. The hypotenuse, how do I find that in general?
The square root.
of x squared plus y squared. Okay, formula number 1. And that is always true. If you give me a rectangular coordinate, I can figure out the radius of the circle that will be on in polar by just doing the square root of x squared plus y squared. So let's do it. Now we can actually try it. The square root of, it's so easy, 1 squared plus 1 squared. 1 plus 1 is 2. There it is. This point right here is radical 2, comma, something. And what's nice is that formula, like that's the formula. That's all you need. Okay. R equals the square root of x squared plus y squared. It just comes right from the Pythagorean theorem. Just plug in the x, y, because they got to give it to us, right? Change from a rectangular point to a polar point. You got to give me the rectangular one. Now, how do we find theta? You know x and y. And we can figure out r, so we could use it, but really, is there a way to figure out theta without even having to do the r equals part? Is there something about that setup, that visual rectangular setup with the right triangle, the theta being a central angle that we open up from, the positive x-axis, like we always have? How do we find the radian measure of that theta right there?
Inverse tangent of y over x.
Inverse tangent. Just like tangent of theta is y over x, right? So maybe you can write that down. Tangent of theta is the simplest trig function that just has x and y in it. Because we need both. I can't use secant, right? 1 over x. That wouldn't work because I don't know what y I'm on. And I want to make sure that I'm taking both x and y into account. So theta is always just going to be the inverse tangent of y over x. And I'm boxing that in because that's the only other formula we need. Now, maybe you can look at a point and know what angle it takes to get there, right? Because the reality of the picture that we're looking at, if that was a right angle, let's pretend, right? This is the triangle that we're in. What's that angle right there? 45 degrees. It's an isosceles right triangle, right? These lengths are the same. This angle has to be 45 degrees. So in radians, 45. 5 over 4. Go out to that circle and up this distance right there, radical 2. That angle right there. And that's how we get there. This would be the answer. That is the point 1, 1 written using polar coordinates. What's up, Dan? How's it going? Okay, so r equals square root of x squared plus y squared. Theta, inverse tangent of y over x. Right.
I'm sorry, I'm still confused on how we got the triangle here.
Theta is the inverse tangent of y1 over x1, which is the inverse tangent of 1. Plug it in the calculator. But we knew that by looking at the triangle that we drew. That has to be 45 degrees. Well, you don't need it. You don't have to know all those things. All you have to do is go to your calculator, press the inverse tangent of 1, and it will spit out, well, in radians, some decimal that means pi over 4. So my advice to you, be in degrees anytime you use inverse trig, because it'll give you a degree measure. I think you can just use it. Let's do another one together. Let's do it together. Okay. Given some points, okay, right in polar coordinates, right? Using polar coordinates, a lot of different ways to say it. Let's go with the points -3, 3. Our goal eventually is to get down to here and have some r theta. That's my hope. Now, to do that, right, we've got formula for r, we've got a formula for theta, but I love to get a little look at what I'm trying to figure out. My suggestion to you, draw yourself a tiny little sketch, just so you know, like once you actually do it, does my answer make sense? Does that angle get me into the right quadrant? Does that length look about right? That kind of thing. All right, so they give us a point, -3, 3, and they say write it in polar coordinates. And what's so nice about this is, you want me to write it like that? I know a formula for r, and I know a formula for theta. And if you know those two, all you have to do is use them. Okay, so to find r, it is the square root of, and I don't have to worry about plus or minus because it's the length of a radius. It's always going to be positive. -3 squared plus 3 squared. Square root of 9 plus 9 is 18. So 3 root 2. The inverse tangent of y3 over x, -3, the inverse tangent of -1. Anybody that maybe has a calculator nearby, go to mode, be in degrees, plug that in. What do you get? It's going to give you, remember, the first angle that it runs into, that's true. It's going to run you into that angle right there of -45 degrees. Is that where this point is? No, it's over here, but you know what this does? Gives you the reference angle. It tells you how far away from the x-axis you are. You are 45 degrees away from the x-axis. Drawing the picture will help you get there. So if this little angle right here is 45 degrees, what is that purple angle that gets you to that spot? The difference between 180 and that angle, 135, in radians. Okay, so our answer is 3 root 2, comma, 3 pi over 4. Okay, we will practice this more tomorrow. I do want to leave you with one other thing while we're taking our notes, one last thing to kind of put on there, and then tomorrow we'll have some practice. There's practice like this on the review that's already posted, okay? But I want to show you how to go the other way, which is not going to be on Friday's test, but good to have written down so that you can come back to it. So before you put things away, I want you to write down one other thing. If I can go to the next page. Be cool? Okay. Really, really quickly, one other thing. I want to show you how to go back from polar to rectangle. Okay, how do we go back from r theta to xy? Well, remember what we've done, right? We've gone out r and over to there. Okay, but I can measure a rectangular distance in order to get there. And of course, it goes back to the fact that the radius of the circle that we're on, I can get to it directly from the origin. Okay? Where this length right here will be x, this length right here is y, that length right there is r. And those are the only things I really need. Okay, and what we've got basically is we get ourselves onto the right circle, right? Am I in the unit circle or do I have to get bigger? Like, where am I? Oh, I'm on that one right there. Okay, x and y take us back to trig. Okay, where x is cosine and y is sine. Right? It's still true, but that's only true in the unit circle. Right? So what if I'm on a circle whose radius is 2, or radius is 3, or radius is 4? Well, I just need to get myself out far enough. R times cosine and r times sine. And that's it. That is how you will get to your rectangular coordinates. I know r and theta. Okay, let's do r cos theta for x and r sine theta for y. You're good. I just want to show you something cool. No, not the whiteboard. I want. Oh, it got me there. Here's the kind of stuff you can do with polar gravity.
I got a 33.25 out of 35 on my test.
Pretty awesome. Pretty
33 out of 0.25.
called the polar rose. It's really cool. That one's probably my favorite. There's a couple other ones that are cool. Spirals. A to the theta. Pretty awesome. You're gonna be here for homeroom? Yeah. Have a good day. You guys are done. Go to homeroom. Don't forget. I will see you mañana. We'll have a review day. Bye, Lynn. Thanks, guys. Have a good one. Go back to the road.
Thanks, Mr. Rosenberg.
You are welcome. Have a good one. What's up, Oak?
I was debating coming today, and I